problem, you have a bunch of clothes which are separated into bins based on color. So you have n colors, and then of each color you have a certain number of clothes, and then you want to wash all your clothes in at most t time. So you want to find the smallest washing machine you can buy that will allow you to wash your clothes in at most t time. So with a washing machine of size X, you can wash up to X clothes of the same color in 1 minute. So for example here, the number of clothes we have of the 4 colors are 3, 4, 2, and 8. So if we have a washing machine of size 3, then I basically represent the answer by summing up a bunch of ceiling functions, because if we think about how we can wash one color of clothes, right? We can't mix 2 colors in one washing cycle. So we have to basically treat each color independently. So if we just look at this first color, then we have to divide the number of clothes by the washing machine size, but then round up. Because if we ever have any leftover clothes, like for example here we have 4, then we have to do an entirely separate washing cycle to wash those. So that's why we round up. So here you see that if you sum up all these ceiling quotients, you get 7, which is just enough to make it. But if you choose something like 2, then you'll see that it sums up to something like 9. So that wouldn't be fast enough. Yeah, here you can just use a washing machine size of 1, and then it will work. So basically, for this problem, let's first consider what we would do if we were just to brute force through all of the possible washing machine sizes. So if we were to try to test a particular washing machine size, we would just basically do this process here. You would sum up all these ceiling quotients and then check whether that washing machine size was fast enough. The time required to wash all the clothes was less than or equal to t. Oh, William, can you mute your mic? Okay, so basically,
it's muted. Okay.
Okay. Now it's good. So we're basically first going to code that solution. We're going to code the brute force solution where we just start incrementing upwards, starting with a washing machine size of 1, and then incrementing upward until we find the first one that works. And then once we find the first one that works, then that'll be our answer. So basically we start at 1, and then it could potentially the highest possible answer that we might want to print is 10 to the 9th, because let's say that all your you have 10 to the 9th of every color, and then t was n, right? Then you would have to have a washing machine size 10 to the 9th. So here we know that these are the constraints. So these are very high. This is a very time-consuming loop. So we know this wouldn't work, but I'm just trying to build a foundation for the solution first. So given us trying to test a particular washing machine size X, we're gonna, I actually didn't read an input. So, and okay, so here I just read in the input, and then to I'm gonna change this to time limit actually. So basically, we're gonna compute how long it will take for us to wash all the clothes with this washing machine size. So I'm actually gonna store this in a long, because even though 1 billion fits, you might add up a bunch of 1 billions if you have a really small washing machine size. So we're just gonna use a long to be safe, and then we're gonna call this time required, and then we're just gonna loop through all the colors, and then for a given color, we want to see how long it would take to wash all those colors. So we want to take the ceiling function, and in Java, as you probably know, doing integer division will basically floor the quotient, but we want the ceiling of it, right? We want to round up, not round down. So what we can realize is that in most cases, when you take the ceiling of some quotient, so let's just some quotient, this in most cases it would just be the floor of the quotient plus 1, right? Because let's say a over b is 3.5, then 3.5 rounded up will be 4, which is 3.5 rounded down, which is 3 plus 1. Right? 4 is 3 plus 1. But the only case where this does not work is if the thing we are flooring or ceilinging is already an int, right? Because then say a over b is 3, then you have 3 equals 3 plus 1, which will not be true. So that's like the only case we need to account for. So in general, we can do time required plus equals the number of clothes of this color we have over the current washing machine size, and then plus 1, right? This will be the floor, and this will we will add 1, but then we just have to check for if it was already an integer, right? If a of I mod x was 0, that means that this part was already an integer, then we just want to undo this plus 1. So we do time required minus minus. Okay, so then now that we have this time required, we just need to check if time required is less than or equal to the time limit, then that means that we can in fact wash our clothes in enough time with this. And then since we are going through the washing machine sizes in increasing order, we know that the first one that we find that works will be the smallest one that works. So then we can just print x and then break. And then this should pretty much work. Okay, yeah, but this will obviously be too slow because it could take 10 to the 9th times 10 to the 5th time, which would be 10 to the 14th, which is very slow. So the observation we need to make in this problem is basically that there's some certain threshold of a washing machine size that will work, and then everything above that size will work, and everything below that threshold will not work. So like I think this should be pretty intuitive for this problem, just because like of the nature of how it's framed, where like it's pretty intuitive that having a larger washing machine will let you wash your clothes faster, right? And having a smaller one will have you wash your clothes slower. So pretty much like if you were to kind of write out a function, like let's say like f of x tells you like f of x is 0 if like if the washing machine size x is not big enough. So pretty much like a bad. So like f of x is 0 if x is a bad washing machine size, and it's 1 if it's good, meaning that like x is fast enough if you chose that as your washing machine size. So if you were to like write out the values of the function, you would get like a bunch of zeros in the beginning, and then at some point it would switch to 1, and then from there on it'll always be 1. So pretty much here, this motivates us to binary search for the answer, because like we're basically looking for the location of this first 1, right? Because that would mean that's the smallest washing machine size that works, right? It's the first 1. So so here we see that like with this linear search solution, there's a lot of wasteful computation because we go through all these zeros when you really only need to be looking for this like breaking point, this breaking threshold. And so okay, let's actually just illustrate how the like the binary search would look. So like you have like a bunch of values like this. Okay, then you're trying to find where this smallest, like the earliest one is. So in binary search, you have to keep track of the left and right bounds. So like at first low will be the lower bound of our binary search will be on the very left, and the very right of the binary search will be on the right. So like we have to make sure in the binary search to make sure that the like desired answer is always within this range, right? So obviously it's within somewhere in the array, this the first one, and like we know it is in the range because like t is at least n. So like in the worst case, we can just make we can make x a very high number, and then just to be able to wash every color in 1 minute, right? So we know there is some 1 here. So then we can just check like the midpoint of low and high. So let's say the midpoint is like this, the 0, and then once we see this is a 0, that means we know everything to the left of the 0 is also a 0. So we don't need to waste our time checking it. And then we have halved the range that we're trying to look over, right? So now we can set our new low to like 1 to the right of the current 0, because we know that like everything starting at this 0 and to the left cannot be the optimal answer. So we can just set our lower bound to 1 to the right of this current middle, and then we can still ensure that the optimal answer is within the range low to high, while still having the range over which we were searching. So yeah, then you would just keep doing this process. So now like the mid, low, and high, let's say just like here, and we see this is a 1. So we know everything to the right of that 1 is a 1. So we don't need to like bother checking that. So we can just set the new high bound to this. And here we don't set it to like 1 to the left of this because this 1 might be actually the leftmost 1. Right here we could set low to 1 to the right of the 0 because the 0 cannot be the leftmost 1 because it's a 0. But this is a 1, so it actually might be the leftmost 1. So we need to make sure to keep it in the range. So we set high just to this exact location. And then next, the midpoint would be here, and then you would see that it's a 1, so you would set high to that. And then here, between low and high, you want to design your binary search to use this as the next middle, and this would be 1, so you set high to this, and then at this point, low is equal to high, so you should terminate the binary search, and then the answer is just low, which is also high. And then that will be the location of the smallest one, or the smallest washing machine size that will wash your clothes on time. So basically, I'm going to start implementing this, and then I'll explain some like implementation details as I go. So instead of doing, okay, I'll just leave that there, but we're gonna declare our lower bound. So we want to make sure that, as I said, our bounds encompass the answer. So so 1 will be the smallest answer that's possible, right? Like a washing machine size of 0, that would just not work. Like you can't wash any clothes. So low is 1, and then high, as I said, it can be up to 10 to the 9th. So that's going to be our upper bound. And then we're going to want to keep doing our binary search as long as low is less than high, because once low is equal to high, then that means that we're done, right? Then low is our answer, or high is our answer, because they'll be the same value. So we need to continue this binary search while low is less than high. And then we're going to guess like the middle, right? We're going to look at the midpoint of low and high and check whether that is a sufficient washing machine size. So we're going to call that cur size, and it's going to be the average of low and high. So here, I'll come back to this detail in a bit, but because this is like an important, both the condition and how we compute the middle, how we compute the midpoint of low and high is important, because it could lead to like having infinite loops. So I'm going to finish coding this, and then I'll come back to like the considerations we have to make for this, because this will actually round down the average of the two because of the integer truncation. But given this current cur size, we're going to do this basically the same thing here. All right, we can basically just copy and paste this code to check whether the current size is sufficient. And then now we're just going to check, like basically do like the same check here. If time required is less than time limit, that means this was fast enough. So that means that like it's a 1, right? So that means that we want to set high to cur size, right? Because like we know everything to the right of the midpoint is a 1, so we don't need to check that. So we can just set high to the current size, and then that will have the size of the range we're looking at without while still ensuring that the answer is within the range. And then otherwise, time required is greater than time limit. That means that like the value we looked at was a 0. So that means we need to set low to cur size plus 1, right? 1 to the right of the current thing we just checked to be a 0. And then again, that will ensure that the optimal answer is still within the range, because by moving low to 1 to the right of the 0, we know that like the leftmost 1 is definitely still in the range because we didn't exclude any ones. So now every iteration of this binary search will have the size you're searching over. So then that'll end up taking a log n time, because which is just much faster than this solution, which takes like n time. So So basically, this is pretty much it. All right, like at the end, like once you break out of the loop, low must be equal to high. So it doesn't matter what you print, low or high, it would work. So here's some details that we need to make sure that we worked out when we write binary search. So basically, low is less than high is a pretty standard like condition to break out of binary search. I think some problems you might want to like, it might be preferable to change that, but it really depends on the problem. You have to really think through the problem. So for this problem, like for this update, you might think that like you might want to do like low is clear size, right? Because you might say like, okay, doing this +1, sure, it doesn't hurt you, but like +1 doesn't really do anything since you're still like having the size of the range every time. So it's still gonna be log n time. So that's true, but the thing is that this will end, if you do low equals clear size, you'll end up with an infinite loop, because let's consider the case where like low and high are 1 apart. Okay, so now when you do low plus high over 2, that midpoint would end up as low itself, right? Then if you go to this else case, then you will set low to clear size, which will be just set to itself, right? So low and high are still the same as they were before, and then that would just keep repeating, right? And then you have infinite loop. So like those are the kind of things that you have to be careful for checking when you do binary search. But yeah, that's pretty much okay. I shouldn't comment this on. But yeah, that's pretty much. Oh wait, okay. Actually, I should probably change these to clear size. So does anyone have any questions over the solution? Yeah, so basically, just as like a recap for the motivation for the solution, we saw that like again, in this problem, it was a bit more intuitive that like there is some threshold of washing machine size that will work. But yeah, in a lot of problems, it'll be less obvious. But I think being able to recognize the binary search is a pretty useful skill, because I think it appears like quite often in problems. And then it's oftentimes more hidden than it was in this problem. Okay, in that case, I will let Daniel present the solution to problem 4.
Okay.